So, lesson 4, independent and dependent events, and the event A and, remember this is going to be our symbol for and, B. The event A and B. So let's start looking at this. Suppose one card is drawn from a deck of cards and it's replaced. So we put it back, we reshuffle. Then a second card is drawn. Let's consider the following events. Event A is the first card is a heart. Event B is the second card is a heart. Determine the probability of A. Okay. Probability of A is going to be how many hearts are there in the deck? 13 out of how many cards are there in the deck? 52. And I know that if I go 13 fraction button 52, it's 1/4 or 0.25. I'm, again, not going to bother reducing fractions in my work. I'll reduce them in my final answers when I'm checking in the back of the book. B. What's the probability that the second card is a heart? Well, because we're replacing it, we've got basically, and reshuffling, a brand new deck. The probability that the second card is a heart is, well, how many hearts are there? 13 out of 52, or 1/4. And again, I told you I'm not going to bother reducing fractions. The probability of the event B doesn't depend on whether or not A occurred. We call this independent events. You want to know another good independent event? Rolling a dice, rolling a die. Whether or not you roll a 6, the previous roll does not affect the next roll. Another good example of an independent event is flipping a coin. Flip a coin, whether you flipped a heads or a tails has no effect on whether you're going to flip a heads or a tails again. So, independent events. Two events are independent if the knowledge that one event has occurred has no effect on the probability of the other event occurring. And I'm going to give you a better definition later. This is the mathematical definition. I'm going to give you one that's easier to wrap your brain around. Dependent events. One card is drawn from a deck of cards and is not replaced. A second card is then drawn. Consider the following events. A, the first card is a heart. B, the second card is a heart. Well, first card is a heart. How many hearts are there in the deck? 13. How many cards are there in the deck? 52. Then part B says, why can't I find this? Well, it depends. Because what I ask myself is, how many successes are there? How many hearts are there in the deck? It depends whether or not I got a heart with my first card. There could be 12 left. There could be 13 left. I don't know. The fact that this number here changes depending on whether A occurred or not. If A occurred, it's 12 out of 51. If A didn't occur, it's 13 out of 51. And the fact that these two are not equal tells you that this is a dependent event. This is a dependent event. A and B are called dependent if the probability that B occurs changes depending on whether or not A occurs. Two events are dependent if the knowledge that one event has occurred changes the probability of the other event occurring. Let's look at some examples. Classify the following as dependent, how about capital D, or independent, how about capital I? Rolling a die and tossing a coin is the experiment. The first event is rolling a 2. The second event is tossing tails. Whether or not you roll a 2, does that change the probability of getting a tails? No. You know what? On a coin, the probability of flipping tails is always 1/2. 50-50 if we go with the odds. 1/2. These are independent. Now, if you look, B and C are almost identical. The key difference is in B, we're not replacing the card. In C, we are replacing the card. Both of them say the experiment is picking 2 cards, and both of them have the first event is that the first card is a king. Second event is that the second card is a king. Well, the probability of the first event in B is how many kings are there. The probability of A, the first event, is 4 kings out of 52. And here, the probability of the first event is 4 kings out of 52. What about event B? Well, in part C, in the third example, because I'm replacing the cards and I'm reshuffling, how many kings are there in the deck? 4 out of 52. I can solve that. It doesn't matter whether or not I got a king on the first one because I'm resetting the deck. But for experiment B, for question B, whether or not I get a king on the second card depends, because I'm not replacing cards. It depends on whether or not I'm holding a king. If I got a king, 3 out of 51. If I didn't get a king, 4 out of 51. Dependent, independent. Basically, if you're looking for a rule, and I'm not a big fan of rules, but if you're looking for a rule, we're saying that, you know what, if you're not replacing the cards, what you're holding in your hand will affect the possible odds or probability of the next outcome. If you're not replacing, they're going to be dependent. If you are replacing, they're going to be independent. Conditional probability. Consider the scenario from the previous page. One card is drawn from a deck and key idea not replaced. A second card is then drawn. Consider the following events. I'm going to do a tree. So over here on the left, I'm going to say, okay, I can have A or not A. Then I can have B, and then here's our notation, given that A has occurred. Or I can have B, given that A did not occur. This is what we call conditional probability. If I walk down these branches, and I'm going to make this a bit bigger here so that you can see this a little easier. So I have B given that A occurred. I have B given that A did not occur. So if I fill in the weights on these branches, there are how many hearts? 13 out of 52. And going down this branch, the probability is 39 out of 52. The fact that we're not replacing now, how many cards are left? It's going to be out of 51. It's going to be out of 51. But down this branch, how many hearts have I taken? 13. So what's the probability the second card is a heart? 12 out of 51. Down this branch, I didn't get a heart. So how many hearts are left in the deck? 13 out of 51. And this is my second definition of dependent events. If you draw a tree and you notice branches that are labeled the same don't have the same probabilities, that tells you that these are dependent. That these are dependent. Now let's read along here. It says the probability of A, 13 out of 52, or 1/4. B depends on whether or not the event A did not occur. We denote the probability of B given A as the conditional probability of the event B given that A occurred. In this example, the probability of getting a second heart, if you know that the first card was a heart, is you got 12 left out of 51. We denote by probability of B given that A did not occur, the conditional probability of the event B given that A did not occur. In this example, the probability of B given that A did not occur is 13 out of 51. And the fact that these two values here are different tells you it's dependent. Let's look at this a bit more. Conditional probability. A red die and the blue die are tossed. So here are the possible outcomes. You can get a pair of ones, you can get a 1 and a 2. Hey, you can get a 4 and a 3. You can also get a 3 and a 4. Here is a sample space showing all of the outcomes. We're going to consider the following two events. Event A, the sum of the two dice is 10. Well, that's that group right there. If I listed it, it would be 6, 4, 5, 5, and 4, 6. Event B is the number on each die is the same. Okay, that's going to be, you can circle this with your pencil, that group. It contains 1, 1, 2, 2, all the way up to 5, 5, 6, 6. Okay. What about the event A and B? What's the overlap? Well, hopefully you can see the overlap is just that. So let's state the following probabilities. What's the probability of event A? That's the one that I circled in blue. 1, 2, 3 circled out of a total of 6 by 6. Out of 36, the probability of event A is 3 out of 36. If you can count it, you can solve it. Hey, what's the probability of event B? Oh, that's going to be, hey, let's do it in green, Mr. Dueck, and be consistent in your color. 6 out of 36. What's the probability of event B given that A has occurred? So, if you know that you're already in the blue circle, in this blue circle, how many are circled by green? How many are part of event B? 1 out of 3. The probability of B given A is 1/3. Hey, let's flip it on its end. What about the probability of A given B? You know what? I should have done that 1/3 in some kind of a different color. I'll do it in black because it's a weird one. What's the probability of A given B? So if you know you're in this group already, given that B has occurred, so you're in here, what's the probability that you're also circled by the blue? 1 out of 6. 1 out of 6. Hey, what's the probability of A and B? Well, how many are circled both times? 1 out of how many grand total? 36. What's the probability of B and A? You know what? How many are circled both times? 1 out of what's the total number of outcomes? 36. Big deal. Actually, here's what we want you to notice. Here's what we want you to notice. It says verify the problem. Verify the following. And means multiply, which we kind of brought up last unit. It says verify that the probability of A and B, which I said was 1 out of 36, is that equal to A times probability of B given A? Hey, look. The 3's would cancel, and I have top times top, bottom times bottom, 1 out of 36. It does work. Verify the following. The probability of B given A is, B and A is, you know what? Again, we're saying show that and means times. Let's see. We said this is 1 out of 36. Does that equal the probability of B 6 out of 36 and the probability of A given B 1 out of 6? Does that work out to 1 over... Oh, look. Again, wonderful. The 6's will cancel, and I get 1 out of 36 equals 1 out of 36. And I say to myself, this one works too. Also, note that no matter what order you do the and in, you get the same answer. Even though the calculations along the way are different, we got 1 out of 36 for both. So this is going to give us another one of our probability formulas. The short version is and means multiply. Oh, hey, here it is. Turn the page. The multiplication law for dependent events. If they're dependent and times. The probability of A and B is the probability of A times the probability of B given that A occurred. Okay. 2 cards are drawn without replacement from a standard deck of 52 cards. Without replacement, that means I'm going to have to keep track of this. Find the probability that both cards are red. Let's find the probability of red. You know what? I should do this in red, shouldn't I? Find the probability of red 1 and red 2. How many red cards are there in the deck? 26 out of... How many cards are there in the deck? 52. And, okay, you picked a red card. You're holding it in your hand. Now you're going to grab another card. How many red cards are left in the deck? Not 26 anymore. 25 out of... And how many cards were left in the deck? Not 52, because you've already picked a card. Multiplying fractions is top times top, bottom times bottom. 26 times 25, 650. 52 times 51. So you can write it as 650 over 2652, or you can use your fraction button. 26 fraction button 52 and 25 fraction button 51. 25 out of 102. That's the probability of picking 2 red cards. Let's try B. Zoom in a bit so you guys can see. Neither card is a club. So what we want is the probability of not club 1 and not club 2. Okay. How many non-clubs are there in the deck? Well, how many clubs are there in the deck? 13. So how many non-clubs are there in the deck? 39 out of 52. And, okay, you picked a non-club. You're holding it in your hand. Now you're going to pick another card. How many non-clubs are left in the deck? No longer 39. You're holding one in your hand. Now it's 38 out of... How many cards are left in the deck? 51. Top times top, bottom times bottom. 39 times 38 over, well, 52 times 51. It's going to be 1482 over 2652. Or in lowest terms, 19 out of 34. C. The first card is a king and the second card is a 5. First card is a king and the second card is a 5. Okay. So we want probability king on the first and 5 on the second. Does that work, I think? Okay. How many kings are there in the deck? How many cards are there in the deck? All right, you picked a king. And, so you're holding a king in your hand, now you want to get a 5. How many 5s are left in the deck? Out of, how many cards are left in the deck? 51. It's going to be 16 over 26, 52. I've kind of memorized what 52 times 51 is because it happens so often. It's 4 fraction 52 and 4 fraction 51. In lowest terms, it's 4 out of 663. Hey, Mr. Dueck, D is the same question, is it? Not quite. How is D different from C? Well, this time they didn't give me a specific order. It just says one of the cards is a king and the other is a 5. I guess that means that we can have king on the first and 5 on the second, or 5 on the first and king on the second. Hey, what does or mean? Add. We already did king on the first and 5 on the second. We said it was 4 out of 51 and, or sorry, 4 out of 52 and 4 out of 51. Now let's do the second one. This time we're going to get a 5 on the first. How many 5s are there in the deck? 4 out of. How many cards are there? 52. And, okay, you picked a 5. How many kings are there? 4 out of 51. Hey, Mr. Dueck, that's actually the same as the other way. Could I have just times by 2? Maybe. Maybe that's a shortcut. But I usually tend to quickly figure out both probabilities. But yeah, it's going to be this number twice because you're just adding it to itself, which is going to be 8 out of 663. And means multiply. What if they're independent? You know what? Independent is actually easier. It's still going to be a multiplication law. It says this: if events A and B are independent, then the knowledge that event A has occurred has no effect. All this means is that the probability of B given A is actually just probability of B. You don't care whether A or B, you don't care whether A occurred or didn't occur. You just need to know what are the odds of B occurring. And so because the conditional portion, the whether or not A occurred, doesn't affect this answer, we simplify it. We just say, you know what, it's still multiply, but you really don't need to concern yourself with whether or not A occurred. As an example, let's draw cards with replacement. So you're putting the card back and reshuffling. Both cards red. Okay. Probability of red 1 and, oh, almost wrote the letter A, and red 2. How many reds are there? 4, Mr. Dueck? How many reds are there? 26 out of 52. And now this time you put the card back, you shuffled up again. How many reds are there? Still 26 out of, how many cards are there? 52. Hey, you know what? It's going to be 26 out of 52 squared. Now, I wasn't sure if I could square a fraction. Let me see if that works. Or does it just square? Yeah, it just squares the 52. So I'd have to go like this. 26 fraction 52 all squared, brackets. Anyways, a quarter. First card is a king, second card is a 5. Okay, so now we're going to have the probability of king 1 and 5 on the second. How many kings? 4. How many cards? 52. And how many 5s? 4. How many cards? You put the king back, so there's still 52. I'm noticing a pattern. Well, it's only going to be like this if each probability is identical. If they had said the first card is a king and the second card is a red card, you would be 4 out of 52 times 26 out of 52. You couldn't square it. But in this case, it's going to be 4 out of 52 times 4 out of 52, or 4 out of 52 squared. It's going to be 1 out of 169. One of the cards is a king, and the other is a 5. Okay, now we don't care about the order. So now we care about. So now we can have either king 1 and 5 2, or 5 1 and Dueck. I'm getting used to this and symbol. I never used to teach it this way. And king 2. Or means add. I already did this. It was 4 out of 52 times 4 out of 52, which ended up being 1 out of 169. How many? Let's do the second one. How many 5s are there in the deck? 4 out of 52. Put it back in, reshuffle. How many kings are there? 4 out of 52. Hey, Mr. Dueck, isn't 4 out of 52 times 4 out of 52 plus itself, isn't that just the same as taking this number and going times by 2? Why, yes it is. 2 out of 169. So whether or not the events are independent or dependent, you know what and means altogether? Multiply. And means multiply. And means, or means add, and means multiply. Now we're going to get a little technical. Well, maybe a lot technical. Students often confuse mutually exclusive. Remember, this means no overlap, or and is 0, doesn't happen at the same time, with independent. They're not the same. Remember, mutually exclusive, if two events are mutually exclusive, they can't occur at the same time. If events are independent, whether or not one occurs doesn't change the probability of the other occurring. Okay, let's get a little technical. You probably might need your formula sheet out for this. If the probability of A is 1/3, and the probability of B is 2/5, and the probability of A or B is 3/5, use appropriate formulas to investigate whether A and B are mutually exclusive or independent. Let's get our formula sheet out. So here's our formula sheet. And I think we're going to be looking at these puppies here. Let's go back to the lesson. Oh, wrong lesson, Mr. Dueck. Make it big again. Dunk. Okay. Show that they are mutually exclusive. Well, what the heck do they mean by mutually exclusive? Well, if they're mutually exclusive, then I guess that means that it's not going to matter whether or not B occurs. Sorry, it's not going to matter whether or not A occurs. Or it's going to mean, you know what, for mutually exclusive, A or B just is add them together. There's no overlap. So here's how I'm going to test this. I have the probability of A or B, and I'm going to see, does that equal the probability of A plus the probability of B? Is that true? Well, the probability of A is 1/3. The probability of B is 2/5. Is that equal to, and it tells me or is that true? Is 1/3 plus 2/5 3/5? No. And you can try it on your calculator if you really need to. 1/3 plus 2/5. But I'm telling you, it's 1/5 plus 2/5 is 3/5. So are these mutually exclusive? No. There must be some overlap. In fact, I can even tell you what the overlap has to be, because the fact that it's not mutually exclusive, what it really means is or was the first plus the second minus the overlap. There's my and. So I have 3 out of 5, 1/3 plus 2/5 minus, hey, let's call it x. How could I figure out what x is? X is going to be 3/5, negative x is going to be 3/5, take away 1/3, take away 2/5. 3/5, take away 1/3, take away 2/5 gives me negative 2/15. You know what? The overlap has to be 2/15. The number that goes right here has got to be 2/15. And the only way for this equation to actually work, if these numbers are accurate, let's assume they are, the only way that or can work by adding is if I go or equals add them together minus the overlap. And the overlap that has to go right there, if I solve for it by minusing that over, and I end up with negative x equals negative 2/15, it turns out the probability of A and B is 2/15. Now let's talk about independent. For them to be independent, and has to equal times them together. So let's see if that works. And, let's write it out symbolically first. And has to equal probability of A times the probability of B. What is and? 2/15. Is that the same as 1/3 times 2/5? Top times top, bottom times bottom. Ah, yes, they are independent. But they are, I should have written back here, not mutually exclusive. There has to be an or for this to work. I don't know if I explained that real well, but let's try a couple of more. So here we go. A and B are events. Probability of A is 1/2, probability of B is 1/3. Okay. And A and B is 1/4. It says, first of all, find the probability of B given A. B, you know what? That's this one. And equals A times B given A. And equals A times B given A. We want to get this. We want to get this by itself. How would I get it by itself? What's the probability of A doing to that? Timesing. So how will I move it over? Answer, divide. The probability of B given A is going to be and divided by A. That's the same equation, just rewritten to get a different term by itself. My physics kids, you've been doing this for a while now. Which is going to be and 1/4 divided by 1/2. 1/4 divided by a half. Dividing by a half is the same as timesing by 2, so this is really going to be 1/4 times 2/4, or a half. The probability of B, given that A has occurred, is a half. What's the probability of A given B has occurred? Well, it's going to be very, very similar, but instead of B given A, it's going to be A given, you know what? If I want A given B, I want a B there. Letter B right there. It's going to look like this. Probability of A and B is the probability of B and the probability of A given B. Same trick. How do I get A given B by itself? Divide. A and B divided by the probability of, this time, because I'm trying to get A and B, by the way, you'll notice this letter and this letter are the same. The given one is on the bottom. The given one is on the bottom. In fact, that's really how I remember how this formula, this particular version works. For conditional probability, if I'm solving for a conditional probability, it's always both and divided by the given one. Both and divided by the given one. Both and, 1/4, divided by the given one, 1/3. 1/4 divided by 1/3, 3/4. Oh, I forgot to, oh no, I did write the full answer there. Yeah. So, probability of A given B, 3/4. What's the last thing they want us to find? Probability of A or B. Well, that's going to be the probability of A plus the probability of B minus the probability of A and B minus the overlap. And you know what? I have all of these. It's going to be 1/2 plus 1/3 minus 1/4. 1/2 plus 1/3 minus 1/4. 7/12. The probability of A or B or both occurring, 7 out of 12. Boy. Staying with me? So far, so good. Example 6. The probability that Sophia will pass math this semester is 0.7. Probability that she'll pass English this semester is 0.9. Oh, and the events are independent. Determine the probability that she'll pass math and English. What does and mean? Multiply. It's going to be 0.7 times 0.9. .63. Math or English. Okay, or means, well, let's use M for math and E for English. M or E. It's going to be 1 plus the other minus the overlap. And it's going to be 0.7 plus 0.9 minus 0.63. .97. So she's got a 97% chance of passing at least one. Or both. So at least one. math and not English. This is going to be the probability of math and not English, which is going to be 0.7 and 0.1. If she's got a 90% chance of passing, she's got a 10% chance of failing. If she's got a 0.9% chance of passing, a 0.1, did I say percent? 0.9 chance of passing, 0.1 chance of failing. Should be 0.07, right? Neither math nor English. Okay, that means not math and not English. What does and mean? Multiply. And by the way, because these are independent, we don't need to get fancy. And just means multiply. Not math, 0.3. Not English, 0.1. Multiply them together, 0.03 or 3%. You know what? I see another way I could have done that. I probably could have used the complement. I could have said the opposite of passing math or English, which means one or the other, or both, is none. I could have gone 1 minus 0.97 and used the complement. Am I going to do example 7? Let me just pause the video for a second here. All right, last one. Sorry, I know it's been a bit of a long lesson here. But let's put it all together. So a number is selected from the first 10 natural numbers. So we're talking about 1, 2, 3, 0. No, it's not 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It says list the sample space. So the sample space, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Event M is a prime number is chosen. Okay. Which of those are prime? 2 is, 3 is, 2 is the only even prime number, by the way. 4, no, 5, 7, that's it. Event N is an odd number. Okay. 1, 3, 5, 7, 9. By the way, are these two sets M and N mutually exclusive, or is there some overlap? I see some overlap. They are not mutually exclusive. Then the third set is M and N. Oh, what is the overlap? Let's write that down. Set M and N. 3 and 5 and 7. And then the fourth set is the union, the combination, the OR. So that's, okay, going to be M-U-N. It's going to be 1, 2, 3, 5, 7, and 9. Right? Right. Okay. State the probabilities of the events. Okay. Probability of M is, well, how many are in M? 4 out of 10. Probability of N, 5 out of 10. I'm just counting. 1, 2, 3, 4, 5 out of a total number of 10. If you can count it, you can solve it. Probability of AND is 1, 2, 3 out of 10. By the way, 5 out of 10 is a half, 4 out of 10 is 2/5, so I'm not reducing because I want to see the pattern here. And probability of M or N, 1, 2, 3, 6 out of 10. All right. Find the probability that a prime number is chosen given that an odd number. Find the probability of P, the probability of M given N. The probability of M given N. Now what you're looking at is this particular formula right down here, formula number 8. I get the letters confused. Here's what I know. This is the probability of and both divided by the given one, the second one. This one is the one that goes on the bottom. That's how I memorize this formula. That's how I understand it. So it's going to be and both over the given one. It's going to be and over, it's going to be 3 out of 10 over 5 out of 10, which ends up being, I think, 3 out of 5. Try it on your calculator, use your fraction button if you need to, but it's 3 out of 5. Then I have a snotty kid named Aiden who says a quicker method for determining the answer here would be to look at the number of odd numbers in the sample space and count how many of those were prime. Or we could have looked at here's the odd numbers. There's 5 of them. How many of them are prime? 3 of them, 3 out of 5. Oh, 3 out of 5. Does that work? Yep. Find P of n given m. Okay, that's going to be and both over the given one. And both is 3 out of 10 over probability of m is 4 out of 10. And if you divide them, I think you'll get 3 out of 4. And now that I see that, I say to myself, you know what? What we're really saying is if you know you're a prime number, what's the probability that you're also odd? Here's my prime numbers. How many of those are odd? 3 out of 4. And I see a shorter way to do it, but I did it the long way and it worked. Whew, that's a lot of stuff. Homework. And you're going to get, I think, some in next class to work on this too. Number 1. So number 2 is one of those weird mathematical, use the formulas. If you get stuck, you can borrow my teacher guide from the front and you'll probably figure it out. Same with number 3. Same with number 4, using the formula. Same with number 5. 6 is good. 7 is good. Although I think physics should be a little higher. Well, whatever. Okay, with replacement, that means this is independent. That's going to make the odds actually a little easier. So 8 is good. 9 is without replacement. You'll notice the questions are identical, except one is with replacement, one is without replacement. So you're going to get different answers. Be careful. %60 have blue eyes. 55% have dark hair. 20% have neither. Okay. This one is tough. I'm going to assign this. I'll probably talk about this when I get back. A standard die is rolled. State the outcomes associated with the following. Sure, this is 11 is good, a good dice question. I would probably make a little sample space and then count. A month is selected at random from the months of the year. Let J be the month begins with the letter J, I guess January, June, July. And Y be the month ends with the letter Y, January, July, May, December. No, that doesn't work. Try 12. Try 12. 13 is good. 14 is good. So I'm giving you everything, but you're going to have class to work on it as well. Make sure you check your answers. Oh, and have a wonderful Christmas break.